Factors that affect solubility. There are three factors affecting the solubility of a solute in a particular solvent. The first is illustrated here by the data in this table, showing the solubility of alcohols in water and in hexane. As we know, water is a polar molecule. Hexane is nonpolar. What we see in the table is that as the molecules get larger, that is, as the number of carbons increases, the molecules get less soluble in water and more soluble in hexane. The carbon part of the molecule is nonpolar, while the OH part of the molecule is the polar and hydrogen bonding part. So, as the nonpolar part of the molecule gets bigger, the substance gets less soluble in a polar substance and more soluble in a nonpolar substance. The first factor that affects solubility is the nature of the solvent and solute. Chemists like to use the axiom like dissolves like. What this means is polar solutes dissolve in polar solvents and nonpolar solutes dissolve in nonpolar solvents. The focus is on the three interactions: solvent-solvent, solute-solute, and solvent-solute. The more similar these interactions are, the more likely one substance is to be soluble in another. Let's look at a couple of examples. Example 1, salt and water. Water has hydrogen bonding. Salt has ionic bonds, and hence the lattice energy. And together, there are ion-dipole interactions. These are similar enough so that salt is soluble in water. Example 2, motor oil, C12H26, and water. Water has hydrogen bonding, oil has dispersion forces, and together there are only dispersion forces. These are not similar enough, so oil is not soluble in water. Further examples. Ethanol exhibits hydrogen bonding, so it is very soluble in water. In fact, it is called miscible because it is soluble in any proportions. Glucose has many OH groups and has significant hydrogen bonding, so it is soluble in water. Where cyclohexane, which is nonpolar and has only dispersion forces, is not. Vitamin A is not particularly polar, so it is soluble in the relatively nonpolar fatty tissues of the body. On the other hand, vitamin C has a lot of OH groups and is quite polar, so it dissolves well in water. For gases dissolving in water, the larger the molecule is, the more soluble it is in water. The larger the molecule, the more electrons, and the greater the dispersion forces, and closer to the strength of the hydrogen bonding in water, so the more soluble the gas is. You should note, however, that none of the gases listed are exceptionally soluble in water, since they are all nonpolar. There are two problems concerning this principle on the problem sheet for this lesson. Pressure is a second factor that may affect solubility, but not of solids and liquids. The greater the partial pressure of a gas, the more soluble the gas is, and not just in water. This is called Henry's law. S sub G equals K times P sub G, where S sub G is the solubility of the gas, K is Henry's law constant, which depends on the gas, the solvent, and the temperature, and P sub G is the partial pressure of the gas. There are two problems involving Henry's law on the problem sheet for this lesson. The third factor that can affect solubility is temperature. Changing the temperature of the solution changes the solubility of the solute. For solid solutes in water, the solubility generally increases as the temperature increases. This is not always true, as you can see on the graph, here shown larger to be easier to read. Because the dissolving of most solids is an endothermic process, most solids are more soluble as the temperature rises. How much the solubility changes depends on how endothermic the dissolving process is. Gases, on the other hand, are all less soluble as the temperature rises. This is because the dissolving of all gases is exothermic. Types of solutions. Solutions can broadly be sorted into types based on how much solute they hold compared to the maximum amount possible. The first type is called unsaturated, which holds less solute than it could at that temperature. If we add another crystal of the solute, it will dissolve in the solution. A saturated solution holds as much solute as possible at that temperature. In a saturated solution, the dissolved solute is in equilibrium with the solid. If another crystal is added, it will not dissolve. In fact, nothing particular will happen to it. What is happening here?
The flask contains a solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution. Focus your attention on the portion of the solution to which the crystal is added. Here is the process again in slow motion.
The movie clip shows the addition of a crystal of sodium acetate to a solution of sodium acetate. It produces a large amount of solid sodium acetate. The solution is neither unsaturated nor saturated, but supersaturated. A supersaturated solution is one that holds more solute than it should at that temperature. Supersaturated solutions that are relatively stable are rare. They are made by heating a solution up and dissolving as much solute as we can at the higher temperature, then allowing the solution to cool. For most solutions, the solute will reach a point where the solution is saturated, and then, as the solution cools further, the excess solute will come out of solution. For sodium acetate and a very few other substances, however, that does not happen. The precipitation of the excess solute can be caused suddenly by the addition of a crystal, agitation of the solution, or any sudden shock to the system.